So this is essentially the proof of Lyapunov stability. It's indeed an amazing result. Why is it amazing? Because, you know, if you look at this particular result, it says some function satisfying two conditions. One is positive definiteness, and the second thing is the so-called time derivative version of this v dot is less than or equal to 0, and both of them imply zero solution is Lyapunov stable, which is in terms of this weird epsilons and deltas, right? So eventually we don't need to worry about epsilons and deltas, we just need to do this condition. And as you can clearly see, we never really solved the ODE to test this particular thing. I mean, it only real condition is basically first we choose a v of x, the candidate, with this positive definiteness, which is independent of the ordinary differential equation. The only other condition that we satisfy, and the single condition, is take the gradient of this v, take the inner product with respect to f, and that has to be less than or equal to 0. And that guarantees Lyapunov stability, right? Stability of the zero solution. And of course, many questions come up, is this absolutely necessary? So for some function like that, do you have to look for a function always, and or is there a simpler method? For the time being, let's assume this is a good sufficient condition. That means, certainly there's a very simple condition to check, and then this guarantees, zero solution is Lyapunov stable, right? If you don't have a Lyapunov function, does it mean it's unstable? Not necessary, right? You could find some other Lyapunov function, things like that. In the end, if there is no Lyapunov function, does it mean the system is unstable? We'll wait for that question to be answered to a later lecture, right? So let's move on. So this is a result on Lyapunov stability. The second one is on asymptotic stability, and essentially we will again look for a Lyapunov function candidate. This time, instead of letting v dot of x less than or equal to 0, we expect this to be strictly less than 0, right? So if you see the result on Lyapunov stability, we can afford less than or equal to, whereas in the case of asymptotic stability, we need strict less than 0, right? So then the zero solution is locally asymptotically stable. So let's look at the proof. Again, we will not go through details. We have, the fact that, sorry, this should have been less than or equal to 0. The fact that, we have this v of x satisfying every condition, only thing this is with respect to strict inequality. Nice thing is basically strict inequality implies soft inequality. So therefore, Lyapunov stability comes for free from those conditions that are apparently important for showing asymptotic stability, right? So what is going on here? Well, okay, we have shown that within this d alpha, we'll remain in, if you start in delta, we will remain there, right? So, but then how do we show that we are going to go to 0, right? So one naive way of thinking about it is v is decreasing, right? There is no doubt about it. And wherever, suppose somehow we assume that it is going to stop here, there v prime of x times f of x is strictly less than 0. That means v dot is 0. So, how can you have some point that you're going to stay there and then v dot is still continuing to be strictly less than 0? So that seems to be a contradiction. But of course, somebody can come and say, oh, how can you assume that this is the way it is, in the sense that the behavior need not be one single equilibrium point, and then could be more complicated. So how do we resolve this? We have this on the trajectory v dot of v dot of x of t on the trajectory is, as we know, it's nothing but this, right? And by integrating both sides, okay, we will get v of x of t minus v of x 0 is basically going to be integral 0 to some t v prime x of t f of x of t dt. Now, uh, you know, let's say I am trying to see this is the delta ball or some other small ball, and then we have this d alpha. So if we start within this delta ball, we know that we remain this d alpha, right? What are we trying to show here? But let's say away from the origin, let's in the region, I'm going to shade this with this thing, including the boundary, let's say. Then we can use this cool um, analysis results, okay, that show that basically this function v of x f of x will have maximum, right? So essentially some maximum, call it L or something like that, L1, okay. So in the region basically d alpha greater than b delta, okay. If we call this as delta ball, for the sake of simplicity, let me put closure. We don't need to, actually it is into the closed set. So how do I know this? Again, it's one of those fundamental results that says every continuous function, which this is, on a bounded set, a compact set, closed and bounded set, it will have a maximum and minimum. So this happens to be minimum, right? So this is equivalent to v dot x f of x less than equal to minus L1, right? Okay. So sorry, this is minus L1, where L1 is positive, right? And then okay, and then minus v prime of x is less than equal to L1, right? Anyway, we'll have an upper bound, something like this, and this particular function therefore can be written as 0 to t minus L2 dt, okay, because this entire function is less than equal to this thing. So I'm going to get this integral as actually minus L to t. So what I got is v of x of t is less than equal to some constant minus L2 of t, okay, where L2 is positive. So this is telling me that eventually v of x of t is going to go to less than 0, because for large value of t, this can become negative. But that's of course a contradiction. Why are we getting contradiction? Somehow we think that basically we can remain within this region d alpha slash b delta. If we remain in that particular region, then this is going to happen, but then that shows a contradiction. It's going to go to 0, less than 0. So we have to enter this particular delta, right? So eventually wherever we start, and then we are going to enter this thing, and then again, we will pick another d alpha, and then we continue this argument, and you'll see that by repeated argument, basically we will have no option but to go to the origin, right? Technically, if you want to prove this carefully, then it becomes somewhat quite tedious, but you get the idea. So by assuming that it's not going to enter this delta region, we showed we will end up with a contradiction. So but then we'll enter a delta region, and in that delta region we can start doing this again repeated version of d beta kind of a thing, and then we'll find another smaller ball and smaller ball and so on and so forth, and eventually we can show that there's no other possibility but converging to the origin. So what did we show so far? These conditions, if satisfied, we get both Lyapunov stability and asymptotic stability. Okay, so exponential stability is relatively straightforward. I will not show the proof in this particular case, but we need v of x to have these upper and lower bounds. This norm could be anything, but in your mind you could think of the standard Euclidean norm, which is square root of x transpose x. and if we satisfy this v prime of f of x less than minus v of x, right? I changed my mind. I'll show you the proof in a second. But something that noticed. So I didn't actually explicitly say that v of x is a Lyapunov function candidate, because this condition v being lower bound of alpha times norm of x actually essentially enforces that it is a Lyapunov function candidate. Okay. So let me again give you a hint of this particular proof. So I have something like v dot is less than or equal to minus epsilon v, right? So if I'm going to multiply with e raised to epsilon t on both sides, okay, I'm going to get something like this, right? So this is equivalent to d by dt of e raised to epsilon t v is less than or equal to 0. By integrating it, we will get e raised to epsilon t v of x of t is less than or equal to v of x of 0, right? And this is some constant, so v of x of t is less than or equal to v of x of 0 times e raised to minus epsilon t. But v of x0 is less than or equal to beta of norm of x of 0 times e raised to minus epsilon t, and this one is alpha times norm of x of t. Okay, that's the first condition that we have. So we end up with basically alpha of x of t is less than or equal to beta times, and I can do this, okay, x0 e raised to minus epsilon t, right? So this is exactly the definition of Lyapunov, exponential stability. Okay, so in that sense, the proof of exponential stability is the easiest. And like I said, Lyapunov function candidate property is automatically satisfied. Much more, of course, if this is true, then this is strictly less than 0. So it also implies asymptotic stability. That shows that, again, one more way of thinking about it, exponential stability always implies asymptotic stability. Now, the notion of global results, is quite important. But before we do that, if we don't have global stability, what can we do, right? So there is a concept of region of attraction, right? So we know that we are locally asymptotically stable, for example. Then we want to know how big is this region of attraction. That means how far can I go in terms of initial conditions. If I start there, will I come back to the point, right? If it is global, then wherever I start, I go reach the equilibrium point, whereas local, we don't, right? So therefore, we have this very important concept of region of attraction, and quite straightforward. Set of all those initial conditions for which the flow goes to 0 as t tends to infinity. It's as simple as that, right? Literally, it's region of attraction. It is the region where all the solutions will get attracted to the equilibrium point, right? Now, finding this region of attraction in reality is not an easy thing, but again, we can use these Lyapunov functions, to define these subsets of region of attraction. We may not get exactly what is the total region of attraction, but by simply taking some beta, a positive number, and then pick all those points where v of x is less than or equal to beta. We call them sublevel sets. We have seen those kinds of sets in the proof of Lyapunov stability, right? So we can clearly see, since we have a Lyapunov function candidate, I mean, this is a Lyapunov function, so it's a candidate and it satisfies the second condition, v dot is less than or equal to 0. Basically, if you start within that region, this v dot is less than or equal to 0, so we will never cross the boundary of that particular region. So this becomes not only invariant set, but it's actually a subset of domain of attraction. So and this is quite useful. I mean, eventually, if somebody wants to control, and there is only way to control is, let's say, locally asymptotic stable. So we actually control the system from to a particular equilibrium point, and then in a time varying system, something like an airplane going through many different set points, different set point will come immediately, and then that particular set point could be made asymptotically stable, and you have this series of set points connected through these domains of attraction. We transition from one domain of attraction to the other domain of attraction. It's simpler said than done, but there is at least intuitive way of thinking about. Basically take this bunch of set points, this airplane is going, and then at every point you have a certain domain of interaction. You don't go unstable, right? You go remain within this region of attraction, and then you kind of transfer to the next equilibrium point, right? So that is one nice way of actually controlling nonlinear systems. So in all such cases, these regions of attraction become quite important. So that leads us to the last result, last couple of results, which is global asymptotic stability and global exponential stability. Now the global results are relatively simple to understand. The same two conditions have to be satisfied, except they have to be satisfied on the entire space of Rn, right? And needless to say, the local Lyapunov stability. I mean, Lyapunov stability is a local notion, and that is bare minimum that has to be satisfied. The only additional condition that we require is this v of x is going to infinity as norm of x of goes to infinity. It so happens that if this condition is not satisfied, you will get those cases where you have this bunch of islands, and then you can escape through one of the other islands and things like that. Technically, it's quite interesting how to prove that this implies always some kind of invariant sets that we spoke about, sublevel sets and things like that, right? So just this additional condition v of x goes to infinity as x goes to infinity, we can show that global asymptotic stability comes, right? What about exponential stability? Well, the same conditions will satisfy as the local case, except this is going to be satisfied on entire space. And so in this particular case, because v of x is lower bounded by this, automatically as norm of x goes to infinity, v of x is going to go to infinity. So that is kind of trivial. So we just require that these two conditions, the local conditions, satisfy an entire Rn, and we get global exponential stability. The exponential stability is a very restrictive notion of stability, but it's the easiest in terms of showing, right? So that brings us to the end of one of the most important lecture in the entire course, I should say, because we have this very complicated notion of stability, right? I mean, in terms of epsilon deltas, and then there's really not a choice in terms of being that complex. I mean, start close, remain close. These, when you mathematize those, when we put mathematical details, you cannot avoid anything but epsilons and deltas, and it's quite daunting to use those definitions to show some system is stable. But Lyapunov, after providing those definitions, provided also the solutions in terms of this beautiful results that we just saw, how to check for stability without ever even understanding, for that matter, this epsilon delta definitions, right? So in the next lecture we will actually see a bunch of examples. Thank you.